Any questions from last class? We started counting, and so there is this sum product rules. So the major example we saw was this throwing balls into bins, right? And there are all these cases, which things are distinct and which are identical. And finally, there was this thing we discussed called counting in two ways. Okay, so using this trick, we can prove, for example, that number of people who shook hands odd number of times is even. And there are many examples you will see later. So that's counting in two ways. This is what we'll call this trick. And using the same trick, we, in a trickier way actually, this proof you still have to complete as a homework, that for any number a and a prime p, you can show that p divides a raised to p minus a by a combinatorial proof. Okay, so you basically have to count number of circular necklaces. Any questions till now? Okay, so we will now do the binomials. Right, this again is just a formality because you have done this in very many ways while you are preparing for JEE. So you have two things, permutations and combinations, that you count. Right, so permutation is so let S be a set of size n, and say you want to pick R elements from the set in an ordered way. It's number of ways to pick ordered R elements. Okay, so in how many ways can you pick R elements, like as a tuple without repetition, from n elements? So this is called counting the permutations. So the count is, for the first element you have n choices, for the second you have n minus 1, and it goes up to n minus r plus 1. Right, so this is the count. And sometimes we can write it as npr. Okay, you are picking R elements out of n elements, but then not as a subset, as an ordered tuple, R tuple. And the second, so this, simultaneously we have defined and proved this expression. I hope this is clear. Second, more complicated thing is combinations, which is picking a subset. So number of ways to pick unordered R elements or equivalently we can say that how many subsets are there. Right, so this is equal to, this is defined, this is called NCR, and what is it equal to? So you do what you did before, right, this n minus 1 dot dot n minus r plus 1, but then since you want to remove the order consideration, so for a R tuple, how many ways are there to permute? That's, it is R factorial, right? It is R factorial again because of the previous formula. So maybe I should write that. So NPN is equal to n factorial. Okay, that's the definition. So from the same formula you get R factorial, so that you divide by this. So you basically associate tuples, R tuples with a subset. And when you do that, then the count shrinks, and you can see that the exact count is this, which you can again write as n factorial divided by R factorial times n minus R factorial. Okay, this is the compact representation of NCR as a function in n and R. So these are called binomial coefficients. We will also use the following notation. Okay, so these are binomial coefficients. Why the term binomial? What is the binomial here? Yeah, so this appears in an expansion. What is that? If you write x plus 1 to the n, if you expand this, then you can show as an exercise that this is sigma n choose r x to the r, all r. Okay, so for r equal to 0, you get n choose 0, which is 1, or for r equal to n, you get n choose n, which is 1, and then for r equal to n minus 1, you get n choose n minus 1, dot dot, for r equal to 0, you get n choose 0. Okay, so this is, since this appears as coefficients in binomial expansion, we call this binomial coefficient. Okay, but this is, so it has both algebraic and combinatorial motivations, and that will be helpful. So yeah, so those are the traditions. So the tradition is that n choose 0 is defined as 1. And what is n choose n plus 1? Yeah, so the only meaningful thing is it's 0 and so on. Okay, so for 0 and negative r's, for negative r's below 0, you define it to be 0. So for negative r, you define it to be 0. And for large r, you define it to be 0. And for 0, you define it to be 1. Okay, usually this is the definition. It makes sense again because of the binomial expansion. Okay, you don't see here x to the negative or x to the n plus 1, except with coefficient 0. So what are the other properties of this function? So you can show that n choose r is n choose n minus r. How do you show this? Sorry? By substituting in the x plus 1 to the n. Or the combinatorial proof. Yeah, so so in the definition of n choose r, the way we started, we said that it's the number of r subsets. So what happens if you take the complement of this subset? That will be an n minus r subset, right? So they are in bijection. From r you go to n minus r, from n minus r you go to r. So this is just by the bijection. Okay. Other property is, what is sigma n choose r for all r? If you sum it up for all the r's, which is interesting, the range is only 0 to n. What do you get? 2 to the n. How do you prove this? Yeah, one way is you just substitute x equal to 1 here. That will work. But then for that you have to prove this statement. So if you have proven this, then you can just put x equal to 1. If you have not proven this, then what you have to do is you can give a combinatorial argument. Right? This is the sum of number of R subsets for all R, which is the same as saying that you are counting all the subsets. There is no R, right? Which is, yeah, there are n elements, either you pick or don't pick. So it's 2 raised to n. So that is the simple combinatorial proof. And similarly, we can prove what is called van der Monde's identity. Which is the following expression. So this is here in this identity you will actually multiply two binomials, so it's more complicated, at least to look at. N choose R times M choose K minus R, where R goes from uh, 0 to K. So M, N and K are given. Okay, so somebody gives you K, N and M, and then you sum up over all these R's, valid R's. So what do you think you will get? Okay, you remember this. So you will get M plus N, choose K. Right, what is the proof? Yeah, so the combinatorial proof here will work, the thing that we did before. We basically, what comes in the summoned, you have to interpret that. So what is that? So this n choose r times m choose k minus r is what you want to interpret. So it is, yeah, it's look like, it is like, I mean also from looking at the right hand side, if it is given to you, you are trying to pick k subset of m plus n, 1 comma 2 comma dot dot m plus n from this big set. You are interested in picking a k subset, a subset of size k. But what this summoned is doing is, it is picking an R subset from, let's say 1 to n, and k minus R from the rest, which is n plus 1 to n plus n. So number of subset of 1 to n times number of subsets of n plus 1 dot dot n plus m. Sorry, this R has parameters have to be put. So R subset and k minus R subset. Right? Yeah, so if so we think of R as a dummy variable, so all possibilities will be of this type, right? Any subset that you pick of the big set 1 to n plus m, some, let's say R many elements will pick from the first part and the rest from the second part, right? So as you go over R, you have counted everything. So this is then sigma of this over all R's will be number of subsets of 1 to m plus n, which you know is m by definition almost m plus n choose k. Is this clear? Right, so by nice combinatorial arguments, you can prove complicated looking expressions, like we did this e raised to p minus a. Now we have this thing here, which looks massive. If you expand this in terms of factorial, you will never be able to complete this. There is another proof that you can give using the binomial expansion. Do you know that? Multiply what with what? X plus 1 to the power n with x plus 1 to the m, right, which you know is x plus 1 to the n plus m. So as an exercise, look at this, okay, stare at this product and then from this reduce the identity. So let's call this theorem. Okay, so this algebraically also you can actually prove this. It's semantically it's the same proof. And okay, yeah, there is an interesting recurrence formula for binomials. Have you seen that? What is it? What is the name of it? Yeah, so this is called Pascal's identity. So Pascal's identity says that n choose R. I mean, basically the binomial is a function in two variables. So if you know for smaller values of n and R, what is the relationship with n choose R, right? So Pascal's identity gives you the expression. It says that if you know n minus 1 choose R, and if you know n minus 1 choose R minus 1, then the relationship between these three is there is just a sum. What is the proof of this? Correct, yeah. So you can just look at element 1. So consider the element 1 in the set 1 to n. So now when you are obviously interested in R subset, right? So any R subset T, either it has X, either X is in T or X is not in T. And then you count these two counts, and then obviously because of disjointness you add them, right? So this is a creative breakup, and then you just use sum rule. Do you use anything else than sum rule? Formally it's an induction proof, right? So you have to use induction here. So by invoking induction, hypothesis, or well, not really induction, because already you can, yeah, by invoking induction hypothesis or just by the definition actually, or definition of this n choose R. What you will get is that n choose R is equal to, so first the sum rule, number of T's such that X is in T plus number of T such that X is not in T. So these R subsets where X is always is, you only have a choice for the remaining R minus 1 elements, right? So that is n choose R minus 1 or n minus 1 choose R minus 1, because this is like you delete the element 1. Okay, so out of the remaining n minus 1, you only need R minus 1. What about the second one? Yeah, here actually 1 is forbidden, so still the domain is of size n minus 1, but you ask for R elements, so you get this. Okay, and the sum of this by sum rule is n choose R. So this is almost by the definition, you only have to see how to apply sum rule. Any questions? So what happens if you use this in a recursive C program? What will happen? Will that program run fast and give you a solution? Yes or no? Why not? Sorry? No, no, it's not about easy or hard. Let's say n is 100 and r is 50. Do you think your C program will ever stop if you use this recursive approach, I mean direct recursive approach? So what this is doing is it is reducing n choose r into 2 branches, right? Next time it will again into 2 branches, sorry? No, base cases you will get to in the leaf, but the recursion tree, every time it is forking out 2 children, and this happens for n steps. The depth of the tree is n, right? So this is like 2 raised to n steps. So 2 raised to n steps programs actually don't stop. For example, if n was 100, then this is 2 raised to 100 steps. And you can see that you will just keep waiting forever, right? And worse with n equal to 200 or n equal to 1000. So this is actually no algorithm, no, at least practically it is no algorithm. So how can you compute it faster? Sorry? Yeah, so what you should do is that since there are only 2 variables n and r, you create a 2-dimensional array. You basically store the values in a matrix. Don't do recursion. Do what is called dynamic programming. Okay, so you remember the smaller values, and then using the Pascal triangle. So actually the algorithm was already there in Pascal's identity. You have this triangular structure, you must have seen that picture. You just follow that triangular, the diagram, and formally it is called dynamic programming, what you are doing. Okay, so you can do this as an exercise. Implement this and compare the 2 algorithms. So so this is what is called a recurrence relation. So let's study those now. This is a major thing. It will appear again and again in various forms. So recurrence and recursion are essentially the same origin. Right? You have some function to compute or some job to do, and you reduce it to a smaller case. So when the function is about counting, we call it recursion. Okay, the function on n is being reduced to function on n minus 1 or n by 3 or n by 2 or whatever. Okay, that relationship is a recurrence. And then it's a very constructive thing because you can just copy that in a recursive algorithm. Recursive C program can be directly written, but usually that program will not be good. Okay, you have to do more analysis to make it good. So recursion is an aid to counting. So this is true both in math and computer science. So yeah, the most famous or the first interesting example of recurrence, I mean, we already saw Pascal's triangle or identity for binomial coefficients. The other is what is called Fibonacci numbers. Do you know the recurrence for that? Yes. Okay. So I'll bring it in a different example. So how that thing practically appears. So let us ask the following question, which Pingla asked in 300 BC. So Achar Pingla's question was that, so he wanted to count how many Sanskrit shloks can be written with a certain property. So the property is that you can think in terms of short syllable and a long syllable. So a short syllable will take 1 unit, say a beat, right? And and a long syllable will require 2 beats. Okay, so suppose in your shlok you only have these 2 types of syllables. Okay, and you fix the total beat of the shlok to be n. So shlok has small syllable, which we'll call L for laghu. Okay, and a long syllable, let's say not small, short. Which we'll call guru. And so long has length 1 and short has length 1 and long has 2. Okay, so think of them as beats. Now, how many shlok are there with beat n? N beats. So number of shlok with number of beats equal to n. Right? If this is not familiar, then how many beats are there? How many shloks are there with 1 beat? That is only short syllable possible, right? So it's only, so n equal to 1, you only have L. So only laghu is possible. How many for n equal to 2? So you can have 2 laghu and you have 1 guru. Right? And so on, you can go on. So for n equal to 3, you will have obviously more options. So you can have 3 laghu, or you can have 1 laghu, 1 guru, or you can have guru and laghu and so on. Right? It's a shlok, so order is important. So since it is under recurrence relations, you want to now express this function in terms of n minus 1, n minus 2 and smaller values. How do you do that? Exactly. So you basically look at a shlok which ends with L and look at a shlok which ends with G, and then those two are disjoint. So you apply the sum rule, use definition or induction to get the recurrence. Right? The same thing you can also do with a musical composition. So there beat will be more applicable. So you want to count the number of musical compositions where the total beat is n, and then there are these smaller parts like 1 beat, 2 beat, 3 beat, and you can express the recurrence similarly. So let's call this function, in a motivated way, we call it L, we call it Fn. Okay, and let us now write the recurrence for it. So these shloks are 2 cases, right? You have ending with L or ending with G. So the count when a shlok ends with L, how many shloks are there? That will be Fn minus 1, right? Because before L, the beats is exactly n minus 1. And when it ends with G, then it's n minus 2, right? So this means that by some rule, Fn is equal to Fn minus 1 plus Fn minus 2, right? And so to get the value of Fn, how many base cases are there? Yeah, since it is dependent on previous two, so unless you fix the first two, you cannot go to the third. So we have to fix, or from first, when you go to second, the second you cannot deduce from this formula. So this formula actually has assumed the following. We did not see it or mention it, but there is an implicit assumption which sometimes you make mistakes. We are assuming that n is at least 2. No, wait, n equal to 2, it's fine. F0 is 0 beats. So there is only one shlok, the empty shlok. So those are the base cases. So F0 is 1 and so is F1. Okay, so with F0 and F1 you can deduce F2 and so on using this formula, using this recurrence formula. Okay, so this obviously is a very fundamental sequence of numbers, and a lot is known about this. There are thousands and tens of thousands of identities written down for this function Fn. So this was rediscovered by Fibonacci much later. In many other examples, not this example of shlok. In I guess 1200. Okay, so you usually see this as Fibonacci numbers, but you can as well call it Pingla Fibonacci numbers. The thing is the same. And there are many, many practical examples where this happens. Any questions about this example? How fast is this group growing? You think it is growing exponentially in n? Like, is Fn close to 2 raised to n? Yeah, you can show that it is actually not 2 raised to n, it's much smaller than 2 raised to n. But is it close to n to the 10? As n grows fast, or as n becomes very large, will it be close to n raised to 10, n raised to 100? Yeah, so it will actually neither be close to 2 raised to n, nor it will be close to n raised to 10 or n raised to any constant. It's somewhere in between. Definitely it is exponential. Sorry? What is phi? Yeah, so we will do that now by, so for that you need generating functions. So for that analysis, generating functions are needed. Now you can see here, if you didn't have experience about this Fn, then from the recurrence you don't learn much about the actual function Fn as a function of n. Right? It is still an abstract quantity. Because you don't have a guess for Fn. So if you first you have to make a guess, then you have to substitute and see whether the guess is right. And that is not very easy because, as I said, there is no reasonable function you can guess for this. So neither is it n to the 10 or even n to the 100, nor is it 2 raised to n, right? So it can be 1.5 to the n, but if you check that, then it's also not close to that. So it turns out to be between 1.5 to the n and 2 to the n, and then it can be anywhere. So what do you guess? Right? So the best way is to not guess and just use generating functions and let this thing automatically evolve and give you the function as exact as you want. So that is why we use generating functions, to find as closed as possible. It will not really be a closed form, but to find a closed, almost closed form expression of Fn. Obviously using the recurrence. So once you have a recurrence, then you can apply a generating function in general. So how will it work? What is the starting point of a generating function? Yeah, so generating function is a complicated thing. It's not very elementary, because you have to come up with an infinite object that is called a power series. So you have to consider a power series. It is called formal power series for some reason, which is let me call it GT. So what it does is that it is just summing up these values all the way to infinity. Okay, so it's like 1 plus t square plus t cube, but instead of 1 everywhere, we have put Fn for t raised to n. Okay, so Fn is the coefficient of t raised to n in this for all n. Now the question, if you are adding something infinitely many times, for example, if you add 1 infinitely many times, what happens? Then it will not make sense, right? It doesn't go anywhere. So how do you say that this thing that we are doing, it makes sense? It is an object that exists. Yeah, so that is one way. You can think of this as either you think of t very, very small, very small real number, very, very close to 0. So if it is very, very close to 0, then hopefully, no matter how fast Fn grows, still the series will converge to something meaningful. But since we don't know where Fn will go, so this is not a very safe bet. Instead, what you do is you just think of t as a variable. Okay, this will be the preferred route, and then it is fine, because we don't expect t to take a real value. We will just look at it as an abstract algebraic object, which is more than a polynomial. So polynomial has to stop at some t power. This will not stop, it will go all the way to infinity. Okay, so these things are called formal power series. Because there is a formal variable t attached, and then you can study properties of this separately. Let me not go into that, because that will be too much of a diversion, and we want to converge. So so you can just read that up. So formal power series is actually, it's a ring, it forms a ring. or they form a ring. Or if you collect all these formal power series, it's an object which we'll probably study in the end of this course when we do algebra. So this is the ring of formal power series. And what it means for now is that you can add two power series and you can multiply, and you will again get a power series. Okay, so it's closed under addition multiplication. I'll drop the term formal. Power series is just now referring to what we wrote, and they can be added and multiplied. And if you multiply power series finitely many times, or if you add them finitely many times, you again get a similar object. You are again in the same domain of power series. Okay, so this will be important to do what we are now going to do with Fn. Right, so now we want to implement this recurrence relationship on GT, right? How do you do that? I mean, you have seen this many times, probably never thought about the proof. So the starting point is that GT is F0 plus F1t plus F2t square. Now if you focus on n Fn, you want Fn to be related to n minus 1, right? So what is done is, and you will see why, you multiply this with t, so you will get F0t, you just shift the representation. It's the same thing. Right, so basically the coefficient of t, if you now look at, you have F1 and F0. Coefficient of t square, you have F2 and F1 and so on. And what's the third step? Yeah, you also wanted Fn minus 2, so you should also multiply by t square. So that will go, then send F0 here. Right, so each of these things are again formal power series because we have just multiplied by a monomial, in fact, t or t square, and now you can add them up with any numbers you want. So here you use the recurrence. So for example, this is the first interesting place where you know the relationship between these three. Right? What is the relationship? F2 minus F1 minus F0 is 0. Right? So that is what you should implement. So that you will get if you write GT times 1 minus t square is equal to F0. I mean, we can just simplify this, right? F0 is what? It is 1, F1 and F0 will cancel, and you will get from here everything 0. Is that clear? So this is a drastic simplification from this infinite object. Now you have a finite one, right? That this is the magic, which means that somehow GT is very special. GT looked infinite, but it is not. It turns out to be somehow finitely representable, and that somehow is, you have deduced that GT is a rational function. It's 1 over 1 minus t square. Okay, so it is not a polynomial, but it is not so good, but it is still somehow inverse of a polynomial, the reciprocal of a polynomial. Is that clear? What do you do next? Yeah, we could stop here, but our original goal was to actually find Fn as a function of n, or at least be able to compute a value of Fn, say very fast on a computer. Right? You want very good handle on Fn. You don't want to do this recurrence for 1000 many times. If n is 1000, you will be doing this the whole day. You don't want to do that. You want a more systematic and a much faster way to calculate. So will GT help in that? So for that you have to try simplifying it. So what do you do? What? Partial fraction. Yeah, you factorize. Yeah, so this is a quadratic. Will this quadratic polynomial factorize? Over what? Sorry? Yeah, over, do you need complex for this? This is t square plus t minus 1, right? So, yeah, so it has actually real roots. So let us factorize it. Should factorize that. So 1 minus t square I can write as 1 minus alpha t, 1 minus beta t. What are alpha beta? Yeah, so that is where you will get these numbers. You can check that. Basically, let's just write in 1. So alpha is 1 plus square root 5 by 2 and beta is 1 minus square root 5 by 2. Is that correct? Okay. So assuming that this is correct, you do your calculation and check that this is correct. So now, how do you plan to use this? What does this tell you about G? Sorry? Right, you want to find the coefficient of t to the n in GT. How do we get to that? Because you know that this is Fn by definition, but we want to compute it in an analytic way instead of the combinatorial way. So what are the steps that you should take now using alpha beta? Yeah, maybe you should look at a simpler question first. Suppose GT turned out to be 1 over 1 minus t. Will you know the coefficients of t? Then you know that 1 upon 1 minus t is 1 plus t square and so on, right? So what you learn is that if you have a linear function in t in the reciprocal, in the denominator, then you can easily find the coefficients. So that is what you should now convert GT to, and for that you will use, is there a name for this? Yeah, so you just try to write GT as a sum of 1 over 1 minus alpha t and 1 over 1 minus beta t. Now why should this be possible? Well, you can just check this. You write 1 over 1 minus t square equal to C1 over 1 minus alpha t plus C2 over 1 minus beta t. So you take the LCM and then you see that you get 2 constraints on C1, C2. So there are 2 unknowns and there are 2 constraints, right? So you can solve it hopefully. So you do this and you will actually find C1, C2. and once you have found C1, C2, you can then write what is 1 over 1 minus alpha t as a power series now. So now you go back to power series because it has become very simple. 1 plus alpha t plus alpha square t square and so on plus C2 times beta t plus beta square t square and so on, right? And what is the coefficient of t raised to n now? Right, so now you can see directly that Fn, which is by definition coefficient of t raised to n in G, is simply C1 alpha to the n plus C2 beta to the n. Is that clear? Okay. Yeah, you can solve this, and this is what you will get. So C1 turns out to be alpha by root 5 and C2 is minus beta by root 5. You can check that, and now if I substitute this here, you will get a nice little expression which nobody could have guessed, which is alpha to the n plus 1 minus beta to the n plus 1 by root 5. Okay, this is true for all n. So in some weird way, you now have computed the function Fn, right? You have complete understanding because alpha, beta are these real numbers. 1 plus minus root 5 by 2. And then you just have to exponentiate them n plus 1 times. Take the difference and divide by square root 5. Now, why will this give you an integer? You are dividing some random thing by square root 5. This itself is very mysterious, right? So you prove those things. Why does it make sense? So this potentially is an algorithm. You can actually implement this, and for very, very large n's, like n equal to 1 billion, you can compute the value of Fn. While if you did this by the recurrence, then that would be 1 billion steps. But here it will be much faster. In fact, it will be more impressive if you look at maybe n to be 100 digits. Okay, in that case, recurrence you will never be able to do one at a time, but this you can implement faster. So this is both mathematically and for computer science a useful expression. Let's stop at this point because other things will become more complicated. We'll do it tomorrow.